So now we're going to introduce a variation on this idea called compressive subspace matching. So to motivate this, let's go back to the simple example where we're trying to estimate this tone using some compressed measurements. So we have some vector, and we'd like to estimate the amplitude, frequency, and phase of this signal. Now we could set this up modeling all three parameters using theta 1, theta 2, and theta 3 to represent this amplitude, frequency, and phase. But this is a little bit unsatisfying as a grid search, as we're doing this over three variables and we have an unbounded search over theta 1. What we could do instead is set it up as a weighted sum of cosine and sine terms, where we just have a single unknown parameter theta and we have some linear weights alpha 1 and alpha 2. And the advantage that this gives us is that we can, for any fixed theta, solve a least squares problem to estimate alpha 1 and alpha 2 without having to do a grid search. And it also handles the unboundedness of alpha 1 and alpha 2 in a very natural way. So classically, we have this set up here is this theta hat. This is just minimizing the L2 norm difference between H and this model term. And in the compressive case, we're doing the same thing, except that we're matching the compressed vectors from the compressed H to the compressed version of cosine and the compressed version of sine with some weights alpha 1 and alpha 2. And again, for every fixed theta, this is just a least squares problem in both cases. And all we have to do now is do a grid search over theta. So these two plots up top represent that. So in the dashed blue line, you see the classical error curve, and in the solid green one, you see the compressive error curves. And we're minimizing them in both cases. And the thing that's remarkable is that this theta bar term here on the left is very close to this theta hat term here on the right. And so this will be a common theme throughout this thesis, is that the classical and compressive cases work very closely together. And here, when m equals 20, we're taking more compressive measurements and they become even closer. Okay, so more generally, the way we're setting this up is we're saying that our functional class is just some parameterized subspace, v theta times alpha. So alpha is just some vector in Rk, and theta just belongs to this parameter set. So f bar is our classically estimated parametric estimate, just using some f from the script f, our functional class. And this is completely equivalent to estimating theta bar just by maximizing over all theta this projection matrix p theta applied to h. So p theta in this case is just defined as the outer product between v theta and v theta transpose. And so also likewise, we can estimate f hat as the minimization in compressive space between h and f, but now we're searching basically over vectors instead of functions. And so theta hat falls out the same way, except now the projection matrix that we're using is not over v theta, it's over phi v theta, which will give us a different type of subspace that we're searching over. The good thing about this is that it handles subspaces gracefully, and these alpha parameters are all estimated implicitly, and so we don't actually have to do grid searches over them. And it's completely invariant to unknown scale in H, which is great for applications like match filtering, for example. But then why are we doing this in the first place? Why are we using this compressive approach? Well, there's two reasons. So one is that it might be easier to acquire phi h than h. This is the reason that's commonly pitched. And a second one that's not explored as much in the literature, but where we use it a lot, is that sometimes it can be easier to compute phi v than v. And we'll talk about this more later. So here's some typical applications. So one of the applications that just kind of jumps out at you is match filtering. So this is very natural to model a shift parameter. Of course, it's a nonlinear relation to the shift parameter, so that's a very natural choice. And LiDAR is just a derivative application off of matched filtering. So here you have match filtering based off of some unknown depth. But all these depths can be very related to each other as well in natural scenes. So over here we have motion compensation. So in between two video frames that can be related by some rotation or some homography that usually have only a small number of parameters that you have to estimate. So you can do something like this very efficiently. And then the application that we'll discuss the most in this thesis is match field processing, which we'll talk about more later. Now there's also other applications we haven't looked as much in yet, but seem promising. So for example, transit detection. Transit detection is a way that we can detect planets, and we do this by waiting for them to pass in front of stars that are way off in the distance. So we have this Kepler satellite that's focused on billions of stars, and so it has to keep track of all these billions of stars. And it's waiting for one of them to just become 0.1% dimmer so that it can detect a planet passing in front of the star. This is something that seems like it could benefit quite a lot from a compressive approach. And also there's ECG monitoring. So here you have a series of heartbeats that you could make compressive measurements of, and the goal is to basically detect bad heartbeats. So you could have some subspace that spans good or natural heartbeats, that's VK, and some subspace that spans bad or abnormal heartbeats, such as ones caused by arrhythmia, and those are defined by this WK term. And the idea is that we want to evaluate this parameterized likelihood ratio to detect bad heartbeats, essentially. And the main idea is that compressive measurements can help you enable these sorts of energy-efficient devices that could be worn on the patient, for example. So now we're going to give a quick overview of the main results, and we'll come back and flesh this out more later, but for now, we just want to give a quick overview. So the main idea is that for any parameterized set of k-dimensional subspaces with this parameter dimension d and a base covering n naught, then compressive parametric estimation behaves very similarly to classical parametric estimation, as long as you take a number of compressive measurements m that's at least k times d plus log of k n naught. And so this approximately reduces to taking m that's at least k log of n naught. So n naught here is just, roughly speaking, it's a measure of the parameter set theta. We'll go into more details later, but for now just think of it as a sort of area or volume of the parameter set. So next we're going to talk about our flagship application in compressive match field processing.